Hello, everyone. Today we are presenting our Lab 6 sensor board and closed loop control PV inverter. My name is Umang. My partners are Andy, Eric, and Tone. The objective of today's presentation is to go through the schematic of the design, key concept of the circuit and board design, major parts and function of the designed sensor board, closed loop control system, and what are we controlling with the microcontroller and the sensor board.
Hello everyone, my name is Andy, and on this slide, this is our overall schematic diagram of our sensor board. The design was generated by two subsystems, which are the voltage sensor that's located on the upper right of the diagram and the current sensor on the bottom. The rest of the components are the voltage sources as seen in the upper right of the image and the 6 pinpoints that link up all together. Our first step was deciding the gain that we wanted for our system. At first, we had several trial and errors and eventually ended up with a gain of 2 through a solution involving the R1 resistors. In this case, R1 is resistors R166 and R157 of the voltage sensor subsystem, and the gain resistors is R153, which is more accessible if needed to be changed. To filter out the unwanted signals, we formulated the filtering using the equation shown on the slide. For our cutoff frequency, that was also used to determine our capacitor and resistor values, which are C99, R94, and R167, located towards the end of the current sensor subsystem.
Hello everyone, my name is Eric. As you can see from the board layout, the 3 power sources, namely V negative, V positive 1, and V positive 2, are located on the left-hand side of the board. One of the key concepts of the board layout is the isolation and the attempt to avoid the trace overlapping related to the current and voltage sensor connections. The 6-pin junction was placed at the center since all the subsystems and components lead to that junction. The capacitors connected to the sources on the ICs were also placed beside the corresponding ICs. On figure 3, we can see the arrangement of the ports on the junction. From left to right, the current sensor, ground, V negative, V positive, ground, and finally the voltage sensor. Next slide. Since we only have 100 kilo ohm resistors, we soldered 2 100 kilo ohm resistors in series for the gain resistance R153. The capacitors C130 and C133 serve as the filters for the inputs of the 2 op-amps. To regulate the output, ratio was used by applying the voltage divider theory using resistors R166 with R151 and R157 with R158. Also, note that the Mark C99 have an almost non-visible 2 100 nanofarad capacitors soldered on top of each other for a 200 nanofarad capacitance to meet the cutoff frequency requirement. Next slide.
For the functions, my name is Toàn Nguyen. For the function of the sensor board, one of the primary functions of the board is a current sensor subsystem. The main component of this circuit is a TMCS 1100A4 chip that allows the current to follow through the 1.8 milliohm conductor and generates a magnetic field, which is measured by the integrated Hall effect sensor. For our design, the current sensor chip reads the current coming between V positive 1 and V positive 2. The same current flowing creates the magnetic field proportional to the input current by the whole sensor IC, which limits the input voltage switching path through the circuit. Next slide.
This is our setup for the connection of closed loop. Pins 40 through 37 are connected to the EPWM interface pins on the control board. Pin 29 on the launch pad is connected to the current sensor. The inductor is connected to V positive 2, and the capacitors and resistors block are connected to V positive 1. Ground pins used in the setup are pins 22, 20, 62, and 60.
So when we tested our system, we did our initial test using just a regular DC power source. As you can see, the current sensor has an output in yellow line, and the voltage output is shown in the green line. For the closed loop control system, we used a PID control that provides a continuous variation of the output with a control feedback mechanism to accurately control the process, removes oscillation, and provides a increasing process efficiency. The result of the closed loop control system can be seen in figure 9. The oscillation is pretty nice, and we reduce the noise we reduce the noise. We use the IRF at 0.5 to get the result. So what are we using the microcontroller and sensors for? The microcontroller is used to process, and it is controlling the closed loop control system. Microcontroller also measures the output continuously and feeds it back into the input. Therefore, it ensures high, more reliable, and stable system and output. The presence of the feedback control of the system for any disturbance and improves the output and overall system. Thank you very much.